Okay, so what we're going to do in this section is look at linearization and Newton's method. So this first part of notes is going to look at linearization. And that's when we're looking for some different things. We're looking for if x is differentiable at a specific point, then the equation of the tangent line is this guy right here. Okay, the linearization L of f of a plus f prime of a times x minus a defines the linearization of f at a. And so the approximation f of x equals L of x is a standard linear approximation of f at a. The point x equals a is the center of the approximation. So that's how we're going to set our first problem. This looks really weird, but basically we're looking for a derivative, and we're looking for a derivative at a specific point. Alright, so using our previous rule that we just talked about, f of a, and let's just write it down here. F of a plus f prime of a times x minus a. Here's our linearization rule. Okay, here's our linearization rule. So find a linearization and use it to approximate 1.0, the square root of 1.02 without a calculator. So we're really interested in f at 0, which is going to be the square root of 1 plus 0, which is 1. That's f of a. The derivative of x is going to be 1/2 times 1 plus x to the negative 1/2. Okay. That's our derivative. And so we want to know the derivative at a, which is going to be 1/2 times 1 plus 0 to the negative 1/2 power. Well, think about what this really is. This is 1 over 2 times the square root of 1, which is 1/2. And so to write our linearization, we take f of a, 1, well, let's say it this way. L of x is equal to 1 plus the derivative at a, 1/2, times the function at x minus a, which is going to be the square root. Let's see, the function at x minus a is going to be 1/2 times x minus 0. And this is going to be your linearization. And it's going to look like, if you wanted to reduce that a little bit more, because this is just, right here, this is just plain old x minus a. So don't make it more complicated than it is. So this is actually going to give us 1 plus x over 2 for our linearization. Alright? So if we want to look at this guy right here, then we're looking at, so what we're going to look at then is we're going to look at the square root. We're going to look at it as the square root of 1 plus 0.02. So what this means is that's my x value. X equals 0.02. And then we look at this whole thing. Well, we've already worked out a linearization for the square root, so we're just looking at the function at 0.02. So we would say that the square root of 1.02 is equal to, and then we take this little x guy right here, the function at a, 0.02, which is equal to the linearization at 0.02. And our linearization is 1 plus x over a, or x over 2, excuse me. And so when you work this out, this is going to be 1 plus 0.01, which is 1.01. Looks horrible, but totally bearable. Okay, so here's another linearization problem, and this time we're interested in what's going on when x is 2. So we're going to look at f of 2, and don't forget what our linearization looks like. Looks like the function at a plus the derivative of a times x minus a. So this is so we need the function at a, which is going to be the cosine of pi over 2, which is 0. Then we need the derivative of x, which is negative sine x. And then we need the derivative at pi over 2, which is negative sine of pi over 2, which is going to be negative 1. So our linearization of x then is going to be f of a, which is 0, plus f prime of a, which is negative 1, times x minus a, which is pi over 2. And so this is going to give us then negative x plus pi over 2 for our linearization. So if we're going to figure this out for the cosine of 1.75, then what we're really going to do is we're going to say, we're going to look at cosine of x again, but we're going to let x equal 1.75. So we're going to be looking at the function at 1.75. And remember, this is our function right here. And if we're looking at the function at 1.75, this is the same thing as looking at the linearization at 1.75. But we just worked through that whole process with the cosine and what it looks like. So what we're going to have is the negative. We're going to basically just use this formula, negative x. So negative 1.75 plus pi over 2. And when you punch it into your calculator, whatever it gives you will be your answer. And when I do it, reach for my calculator here. So I've got negative 1.75 plus pi over 2. I get negative 0.1792. So that's our approximation, and that's how you do this. Not too bad. So a result of linearization is this little guy right here, and what it is a relationship between the linearization of a function and a power, and especially if you have a small value of x, so 1 plus x to some power. So on all of these, we could do all of these very simply. We just need to make sure that they're all written with a plus sign and to the appropriate power. So that guy would look like this. This one would be 1 plus negative x to the negative 1. Now this guy's a little bit different, but he would be 1 plus 5x to the 4th to the 1/2. And then this guy would be 1 plus negative x squared to the 1/2. So we need all these guys negative 1/2 written in the correct form. And then once we've got it in that form, we just follow the rule. So when I go to linearize this, I'm just going to have the exponent times whatever the x is. So 1 plus 1/3 times negative x, which is 1 minus x over 3. That's it. That's all there is to it. This guy would be 1 plus negative 1 times negative x. So this guy's just going to be 1 plus x. Down here, this would be 1 plus 1/2 times 5x to the 4th, which would be 1 plus 5x to the 4th over 2. And then this guy would be 1 plus negative 1/2 times negative x squared, which would be 1 plus x squared over 2. That's all there is. That's all just pattern recognition. Okay, so let's use linearization to solve out the square roots of 123 and the cube root of 123. And when you're working out a square root, remember that your base equation is the square root of x. And when you're working out a cube root, your base equation is x to the 1/3. So we need to keep these two things in mind. And then we just need to think about what we know about square roots. Like, I know that the closest square root to 123 is 121. And the square root of 121 is 11. So I'm going to start here. I'm going to let x equal 121. And so then f of 121, and we just saw this, is 11. And the derivative of this guy, and remember this is x to the 1/2, so the derivative of x is 1/2 x to the negative 1/2. And then the other piece of information that we're going to need is the derivative at 121. Well, the derivative at 121 is 1 over 2 times the square root of 121, which is 1 over 22. So now we just substitute all of this stuff back into our linearization rule, and we'll be able to get our answer from there. So we're going to take f of a, which is 11, plus the derivative at a, which is 1 over 22, times the x that we're interested in. Well, the x that we're interested in is this guy right here. We're interested in this x right here. So we're going to mark him off as 123. And then where are we? We are at 121. And so when you punch all this into your calculator, you're going to end up with 11.09, and that repeats. So this is your linearization then for that particular problem. Not too bad. Well, we could take the same steps then and figure out what the linearization is, or the approximation is, for the cube root of 123. And the closest cube root that I can think of, and we want it to be close because the closer we are, the better the approximation, is 125. And so the cube root of 125 is 5. So we're going to let our x equal 125. And so we need f of 125, which is 5. We just saw that. We need the derivative of this, which is 1/3 x to the negative 2/3. And then we need the derivative evaluated at 125, which is going to be 1/3, 1 over 3 times the cube root of 125, which is going to be 1 over 75. So there's those guys. And then we just apply our rule of linearization to this. So we're going to have 5 plus 1 over 75 times the point we're interested in, which is this guy right here. So that's going to be 123. 123 is what we're interested in. So that's going to be 123 minus 125. And then when you work this math out, you're going to get 4.973. And again, this is an approximation of the cube root of 123, which makes sense because the cube root of 125 is 5.